Okay, so in the last video we learned what Riemann sums are. Just to reiterate, a Riemann sum is a method that we use the geometric shape of the rectangle to approximate the area bounded between a curve and the x-axis. We call that area under the curve. So we learned three different types of ways to do this, or three different types of Riemann sums, those being a left Riemann sum, a right Riemann sum, and a midpoint Riemann sum. So let's look at a specific example of how we're going to use a Riemann sum to approximate this integral right here. Now remember that this integral represents an area under a curve. So when we see this symbol right here, what this really means is approximate the area under the curve of x squared between x equals 1 and 2. And this says with n equals 4, meaning 4 subintervals or 4 partitions. And here we said equally spaced. Remember that in Riemann sums, we can make our area be equally spaced, but they don't have to be. So if we look at an example of a left Riemann sum, remember that the point at which the left corner of our rectangle hits the f of x curve is what dictates the height of our rectangle. So in this case, our base is going to be delta x, which is the same for each rectangle. Our height of our rectangles are going to be calculated by these leftmost x values of each of our 4 rectangles. So for example, this height, this squiggly line, would be x sub 0 or f of x sub 0 for whatever this function is. If we want to find this height, that would be f of x1, and then et cetera, you would keep finding those. So if you want to calculate your area, we are just going to say, for example, the area of this first rectangle would just be f of x0 times delta x. Okay, that's base times height. That'll give us the area of our rectangle. So using that, let's look at this function. Here we have the function y equals x squared. And we have that function defined from x equals 1 to x equals 2 with 4 partitions or 4 subintervals. Notice that this orange area we have right here represents 4 rectangles. Now I know the ink I'm drawing is overlapping those rectangles, but trust me, those represent 4 equally spaced rectangles. So this is a left-hand Riemann sum. Try to see if you can calculate what the area of those regions are, of those 4 shaded regions. All right, if you've done it, you should have gotten an area of 1.96875. So if some of you guys didn't get that, let's first look at how we find the base of each rectangle. Remember, if we have n equals 4, we're starting from a equals 1, we're ending at b equals 2. We'll find the base of each one of our rectangles is just going to be b minus a over n, or 2 minus 1 over 4, which is 0.25. So that's going to be the base of every one of our rectangles. That means, therefore, this x value will be 1.25, this x value will be 1.5, and that x value will be 1.75, okay? So that gives us our 5 important x values for calculating the Riemann sum. So, for example, if we want to calculate the area of this first rectangle, we know the base is 0.25. The height is, again, going to be this leftmost point plugged into our function to get this height, which in this case will be 1 squared. Remember, we're squaring it because our function is x squared, okay? The height of our second rectangle, therefore, would be 1.25 squared, okay? If you don't get that, rewind the video, watch it again. You know, I don't want to spend too much time on these calculations of Riemann sums because really all we're doing is just calculating areas of rectangles. The only thing that's different between Riemann sums is how we get the height of our rectangle, and that's going to be determined by whether we have a left, right, or midpoint Riemann sum. So if you go through and calculate all of this area, you should get, again, this value of 1.968. Keep doing this until you figure out how to calculate that area. It's very important. If you are not able to get this number after watching the video, talk to one of your friends if they were able to get it, or come into class and be like, look, I just straight up could not get 1.96. What are you doing? And when you go over it, I think you'll find that it's very, very, very easy. Again, all we're doing is we're just saying base times height for each of our 4 rectangles. If you're getting this number wrong, you're most likely not calculating the height of that rectangle correctly. So that's a left Riemann sum. So now let's go look at a right Riemann sum. Let me clear the ink from this page. And if we go to the next slide, we'll see in a right Riemann sum, again, what we're doing is instead of using that leftmost point, we're going to use the rightmost point to calculate the height of our rectangle. So therefore, this squiggly line, this height of our first rectangle, will be f of x1 instead of x0. Notice that x0 doesn't come into play here anymore because we don't need to use that x value to calculate the height of any rectangles. All right? The height of this rectangle would be f of x2, and then we would keep finding the heights of all our other rectangles based on things like this. So let's go back to the Desmos file and let's do that exact same calculation we just did, except instead of using a left Riemann sum, try using a right. So try to, again, use a right Riemann sum on the same function y equals x squared between x equals 1 and x equals 2 with 4 subdivisions. Try to do it with a right Riemann sum. All right, if you've done that, if we look at what that Riemann sum will look like, these are what all our rectangles look like. We will end up getting an area of 2.71. Again, if you couldn't calculate that area, let's just look at what the area of the first rectangle would be, okay? Again, area is base times height. We know the base is 0.25. We found that in the last video. The base isn't going to change. We still have 4 equally spaced subintervals between x equals 1 and x equals 2. That means the base of each will be 0.25. And the height of this one, instead of being 1 squared, we're going to look again at that rightmost x value, which is 1.25. So the height will be 1.25 squared. So that's just the area of that first piece right there. Now if we repeat that same process 4 times, changing the height of each of our rectangles, we'll end up with this number 2.71. Again, it's very important that if you didn't get that number 2.71, you keep rewinding the video, rewatching the video, recalculating it until you can get that number. Once you get that number, again, I think you'll all realize that this is just a very, very easy process. Once you get it down, Riemann sums are not hard at all. You should be begging to get a Riemann sum free response problem on the AP exam. All right? So we've gone over left Riemann sums, we've gone over right Riemann sums. Let's go over the one that tends to be the trickiest, and that's the midpoint Riemann sum. So notice with the midpoint Riemann sum, it's not the left or the right corner of the rectangle which dictates the height of the rectangle. It's actually when the center of the rectangle touches the curve. And that's what's going to dictate what our height is. So what we need to do in this case is to calculate our height. We need to calculate that height by utilizing an x value that's in between the left and the right x values of each of our functions. So you'll see the ones I'm circling right now. These are the x values that we want to find. So we want to find an x value in the middle of each one of our subintervals. So let's try to do the same thing. Let's go back to the Desmos plot and clear the ink here. And I want you to now do this Riemann sum using a midpoint Riemann sum. Okay, give it a shot. All right, if you've done it, you should have gotten the area was 2.32. So if you didn't get that area, remember now we're going to calculate the height of our rectangle by an x value that's in between, in this case 1 and 1.25. Well, the x value that's at the middle of 1 and 1.25 is 1.125. So if we wanted to calculate the area of that first rectangle, that would be 0.25 times 1.125 squared. Remember, we're squaring it because our function is y equals x squared. If our function was sine of x, we wouldn't be squaring all these x values. We would be saying 0.25 times sine of 1.125. So again, the squaring has nothing to do with some fancy area calculation. We square it because our function is x squared, okay? If our function was anything different, we would be doing something other than squaring those x values to find what that height is. So that's another example. If you go through this again, if you look at how we calculated this first area and do the same thing for all 4 of the other areas, you should get that number 2.32. Again, it's very important that you keep doing these left, right, and midpoint Riemann sums that are in these examples until you can come up with the numbers that I came up with right there. All right, that's the best way to learn them, is to do them yourselves. Now, there's one more important thing about Riemann sums, and that's that, as you notice, a Riemann sum is only going to give you some approximation of the area under the curve, and that approximation can actually be what we call an over approximation or an under approximation. So let's look at this left Riemann sum on this function we just looked at. It turns out this is an under approximation because if we look right here, we have all these areas, these white regions right here, that are basically area that we are not accounting for. That is actual area under that curve. We would have one right here too. So in this case, a left Riemann sum is actually providing us with an under approximation because we're not including that area that I just showed in the squiggles. But if I change, let's make that go a little bit to the left, like -2. If we change everything, now notice that our left Riemann sum, it still under approximates right here, but now it over approximates when x is less than 0. So can you see anything that changes about the function between, when we're less than x is 0 or greater than x is 0? It turns out that right here when x is less than 0, our function is decreasing. So f prime of x is less than 0. Here our function is increasing, so f prime of x is greater than 0. And it turns out whether or not your function is increasing or decreasing determines whether or not a Riemann sum is going to give you an over approximation or an under approximation. In the case of a left Riemann sum, we see that left Riemann sums over approximate when our function is decreasing, and they under approximate when our function is increasing. All right? If we look at right-handed Riemann sums, we see that the opposite effect happens. So if I make this a right-handed Riemann sum, you see that a right Riemann sum under approximates when the function is decreasing and over approximates when the function is increasing. So that's just the opposite of a left. So basically, as long as you memorize when either a left Riemann sum or a right Riemann sum under approximates or over approximates, you basically memorize what the other one does because they just flip-flop. They're just the opposite of each other. Now for a midpoint Riemann sum, there's nothing to tell whether that's going to give you an over approximation or an under approximation. You just don't know. So if we go back to sum up what we just talked about in terms of over approximation or under approximation, what we have is that a left Riemann sum overestimates decreasing functions or functions where the derivative is less than 0, and it underestimates increasing functions. And then the right Riemann sum does the exact opposite. The mid Riemann sum, we have no idea. So again, rewatch this video if you were having problems calculating what those Riemann sums were. We'll look at some examples in tomorrow in class, but it's very important. Come with questions if you weren't able to calculate those approximations along with the video.